Hello everyone, my name is Fiona and now I will talk about how to powering from phi to psi t to increase the fraction of violated constraint. And so basically I will try to prove the lemma 22.5. And by psi t we want it to be satisfy four properties. So the first one is psi t is also to see P with W prime much smaller is bounded by W over the D over phi t. And also it has D and D over 2t plus 1 constraint. And the second property is that if I is satisfiable, then so is psi t. The third property is that for every basically want to, if value of then so basically the third property is according to increase of the violation fraction. And finally, the transform from phi to psi t need to be done in time polynomial in m and w over d over t. So first we need to construct a psi t. So basically the psi t will have the same number of variable as 5, and the new variable of psi t will be y yn, which takes value from alphabet of size w prime, which is now we declare it equal to w over d over 5t. So basically for every variable yi, it has d over 5t tuples. That takes value from 0 to w minus 1. And now we want to construct a graph that we want to assign assign uj from yi in a way that if the node is indicated for I, then I will assign j that if only if it's in t plus square root t steps. So basically, I will assign the uj if only if the j is in this radius, in this ball with radius of t plus square root t. So for each I, then there will be at most d over t plus square root t plus 1 nodes that may be in this range, because it's the regular graph. And thus we can conclude that since it's smaller than d over 5t, then we can conclude that this can be encoded in the size of w prime. Okay. However, this has some problem, is that if there's another I, and there's might be some jz in both of the range, and thus may have inconsistent assignment. So now I will talk about how to overcome this. So basically, we want to add some constraint to avoid the inconsistency. So in a graph for every 2t plus 1 pass, we declared the starting point as I1 and endpoint as I2t plus 2. So this is 2t plus 1 step. So for every 2t plus 1 step, there must be 2 points that we call this ij and ij plus 1. Then ij is in the range of is in the ball of I1, and ij plus 1 is in the ball of I2t plus 2, and there's only one step between it. Oh, and also ij is t steps from I1, and ij plus 1 is t steps from I2t plus 2. And so that we want to add a constraint CP that it will only depends on yi1, yi2t plus 2, that it will return false if only if this node is in this range, which means ij is in t plus square root t radius around I1, and this node is in range of I2t plus 2. And finally, this pair, if we denote W as the values that yi1 give it uij, is the case, then if this pair of value violates some constraint in 5, then we will output a false. So basically, the constraint means that if there are any violations in this 2t plus 1 steps, then we call a violation of constraint. So basically, there will be, since our graph is irregular, then we would have n times d to 2t plus 1 constraint, which satisfies the first property. And also, from this point, you can see that it's trivial that if polynomial time to produce in W over D over T. So it's trivial that it satisfies the property of 4. And according to this kind of assignment, we can also see that by using some canonical assignment for the new variable, we can also get that if phi is satisfiable, then so is psi t. And then we can then see that it will satisfy the second property. So that's for finally the third one, which is also the most important one. So before getting to prove the third property, I'll first talk about the polarity assignment. Since what we want to do is to make sure if U violates few constraints, then Y will violate many of constraints. So what we do is fix some Y and fix an arbitrary in this variable, and for every UI, since we have this graph, then if the UI will be assigned for a value for any in the radius of 2t plus 2 t plus square root t steps. Thus, we can see that for every node that has distance of t, then it will assign the value for UI. Then we'll call this Z I as the distribution of different assignment for this UI. And for smaller Z, Zi, we will declare Zi as the most frequent assignment in this radius. And this kind of assignment is called polarity assignment. And since we want to prove this property, so we want to find a set of F that has this much constraint inside that violates by this polarity assignment. So that finished the part 2, and Fang-Yi will talk about how to prove the rest of this part. Thank you.